Good everyone. This is Kinematics P1 Practice, and let's begin. So the first MCQ says that the diagram shows the velocity time graph, which is this one. What is the displacement during the last 2 seconds of the motion? So the displacement is the area under the velocity time graph. We have studied this. So this area is the displacement. So let's just apply the trapezium formula. 1/2 times 6 plus 12 multiplied by its height, which is 2. So this becomes 18, right? Because this cancels out and this remains 18. So this is our first answer. Now, a ball is released from rest above a horizontal surface and bounces several times. The graph shows you how for this ball, a quantity y varies with time, right? So we don't know what y is. And the ball is thrown. A ball is released from rest above a horizontal surface. So the quantity y must be, so it can't be acceleration, right? Because this is obviously the point where the ball is hitting the ground. So the acceleration can't be non-zero value when the ball hits the ground, if that makes sense. No, that I was talking about velocity. Velocity can be 0 when the ball hits ground, because the velocity at that time would be 0 for a few seconds, right? Now, kinetic energy, it can't be kinetic energy because this is obviously the points where the graph is hitting the ground. I mean, it could be kinetic energy, right? It could be, but the graph of just leave kinetic energy for now because it's not a energy question, it's a kinematics question. I'm not going to go into too much detail of why it's not kinetic energy. Now, the acceleration, the difference between acceleration and displacement at these points. Now, the acceleration at the point where the ball hits the ground would change directions, right? Because the ball goes down and then it moves up. So the acceleration at this point must be changing direction from here to here. Now, at this point, the acceleration is not changing direction. In other words, sign. So it can't be acceleration. So it has to be displacement, right? Going once again, it's not acceleration because the value of acceleration is not changing signs, right? It can't be velocity because at the ground, velocity must be 0. So it has to be displacement. And why, the reason why it's not kinetic energy is, I'm not going into that a lot because you haven't studied this. So let's just move on. Now, a small steel ball falls freely under gravity after being released from rest. Which graph best represent the variation of height with time? Now, it free falls, the height above the height edge of the ball decreases, right? Because the ball is falling from a height which is decreasing. So this is wrong. One of these three is correct. Now this graph here is also wrong. Let's just discuss A first. Because the height does not decrease uniformly, right? It is decreasing at a gradient because the speed is also changing. So this gives us an expression of constant speed, right? Which is not true. The velocity is not constant. The acceleration is always changing when the ball is free falling, right? Now, which way is it changing? Now, in these two, this here represents an increasing acceleration, right? Increasing acceleration because the gradient is increasing, so the velocity is increasing. And this one depicts a picture of decreasing acceleration, right? Because the height takes longer time to decrease as it goes on, right? So this would be our answer because acceleration would decrease due to air resistance. So a projectile is fired at an angle alpha to the horizontal at a speed u as shown. Now, what are the vertical and horizontal components? Assume that air resistance is negligible. So the horizontal component would be very simply u cos alpha, right? U cos alpha would be horizontal component. So this or this, right? These two are wrong. Now, what is the vertical component? Now, the vertical component, we have only two options here. U sine alpha, which is okay, but after time t, we are not taking an initial component. We are taking a component after a specific time. So because of the deceleration due to gravity, right, the vertical component would decrease. So this is the initial vertical component. This is not the answer. This is the right component because it's subtracting the value of some velocity, and we know this is a velocity because acceleration is g, right? v2 minus v1 divided by t. So gt is the velocity, right? So it's a v2 minus v1. Let's just write it as velocity, right? So this is our answer. On a particular railway, a train driver applies the brake of the train at a yellow signal, a distance 1 kilometer from the red signal. So this is yellow signal. This is the red signal, R, and the distance here is 1000 meters, right? Because we have to consider standard units in our calculations. The max deceleration of the train is 0.2 second. So acceleration is negative 0.2, right? If we are considering this to be the right direction and positive direction, so this must be negative, right? Because the train is stopping. Let this be the ground here, right? So this is the train. Now, this is our deceleration, negative 0.2. What is the maximum speed of the train at yellow light, right? Now, we need to stop the train. So velocity here is v is equal to 0. So to solve a question that requires the application of a kinematics acceleration formula, right? The first thing you need to do is just write everything that you have and the thing that you don't have. So acceleration is negative 0.2. Displacement is 1000 meters, right? Because it's a straight track. So displacement is 1000 meters. V is equal to 0 because it needs to stop. And u is the thing we want, right? Because what is the maximum speed, safe speed of the train at the yellow signal, right? So this is the initial speed, right? That the maximum initial speed that we need. So this is everything that we have. Now, what is the formula that relates all of these quantities together? The formula is v square is equal to u square plus 2as, right? Yeah, that's the one. V square is equal to u square plus 2as. This is how you choose which formula to apply, right? So v square is 0. U square is, let's just put x square plus 2 times displacement, which is 1000, times negative 0.2. And this becomes negative 2 times 1000 times negative 0.2. See how the minus sign nicely cancels out if you put it the right way. So this becomes under root 400 to x, and x becomes 20. So this is the answer. Moving on. Now, a stone is thrown upward and it follows a curved path, right? This is the projectile motion that I've been talking about. And this is a great base for why this MCQ is a great base of why this type of motion happens. So let's begin. Air resistance is negligible, right? So this component of velocity is never affected. Why does the path have this shape? So the parabola shape, basically. The stone has a constant horizontal velocity and a constant vertical acceleration, right? Because this is not affected, just like I said, and there's an downward acceleration of g, and this is the horizontal component v, right? So this is the answer. Let's just go through the wrong answers and strengthen our concepts a little bit more. The stone has a constant horizontal acceleration. Yeah, it does have a constant horizontal acceleration, which is 0, right? So this is true, and constant vertical velocity, and this is not true. So this is wrong. I mean, it does have a constant acceleration in the horizontal direction, right? Which is 0, but that doesn't really explain why the motion is like this. Even if it wasn't, right, even if this had a deceleration, the path would be something like this, right? It won't be that open. It wouldn't have been that open, but it would be something like this. So it would still be this shape, but because of this acceleration, right, that is the main cause of this, right? This in the horizontal direction in one direction, and the acceleration in the perpendicular direction, a constant acceleration in the perpendicular direction. The stone has a constant upward acceleration. No, this is just plain wrong. The stone has a constant upward velocity. Nope, because due to the g, the velocity of upward direction is always changing. Now, a stone is thrown upward from the top of the cliff, right? So let's just draw it, right? Thrown upward initially. After reaching its maximum height, right? This reached its maximum height. It falls past the cliff top, right? It falls past this into the sea. Let's just assume the sea is here. This is the cliff, and the stone falls here. The graph shows how the vertical velocity of the stone varies with time, right? Where the upward direction is positive, right? So in these MCQs, when they don't tell you which direction is positive, you have to assume that the upward direction is positive and the right direction is positive, right? So this is the velocity. This velocity is still here, right? The max point where it becomes 0 and starts to go downward because of the acceleration, right? This is all happening because of the acceleration of gravity. So it becomes 0, and then it becomes negative because it's in the negative direction, right? So this area is basically this length S, right? S is basically this length or this displacement, and R is basically this, right? Because R tells us it goes from this 0 to this when it reaches the ocean. So what is the height of the cliff top above the sea? So we need to find this height, right? So this height is this R, bigger R minus S, right? Because R is here to here. This is R, right? And this is S. So R minus S would be this height, right? So it's R minus S. Sorry for the messy diagram, but you get the idea. Now, which displacement time graph best represents the motion of a falling sphere, the initial acceleration of which eventually decreases, right? Eventually reduces until it begins to travel at a constant terminal velocity. So falling sphere, right? So falling sphere, displacement is increasing, right? Falling sphere, so it's getting more and more displaced, right? Then what happens is the first thing you need to understand about the graph is displacement is increasing, acceleration is decreasing until it reaches 0 because it's at a constant terminal velocity at the end. So velocity constant at the end. So the graph constant velocity would mean straight line, right? So now let's look at the graphs. So in this one, the displacement is going to 0, and this is just plain wrong because the displacement never goes to 0 when a thing is dropping from a height to the ground, basically, right? Yeah. In this one as well. So these are the two remaining. Now, the first graph shows us a great example of acceleration decreasing, right? Acceleration decreasing, decreasing, decreasing. But this part here means zero velocity, right? Because the gradient here is zero. And this is wrong. There would be a velocity, right? Because the stone doesn't just start hovering when the acceleration goes to zero, right? It doesn't just start hovering in the air. It keeps going down, but with zero acceleration. So this graph is the answer because it depicts the decreasing acceleration, and then the graph becomes constant. So this is the answer. Now, a boy throws a ball vertically upwards. It rises to a maximum, right? This is the boy. Throws the ball, goes to maximum height, where it is momentarily at rest, right? Because this is the maximum point where the velocity is zero, and falls back to his hand, right? Then falls back to his hand. So which of the following gives the acceleration of the ball at the way? Now, the reason I have selected this MCQ is to give you a concept of G. Now, at one point, when the ball is going upwards, the ball is slowing down, right? Because the acceleration is in the negative direction, which is G. Now, at the second phase of the thing, you know that this acceleration is G, which is 9.81, negative 9.81, because it's going downwards, right? Because the acceleration is downwards. The next phase is the stationary phase of the ball, where the ball is at zero velocity. But even though its velocity is zero, it is still experiencing the acceleration of G, which is negative 9.81. And then moving downwards, obviously it's increasing in speed, and the acceleration of it is negative 9.81. So this is the answer. So the reason I selected this MCQ is to make you understand that acceleration in free space around the Earth is always negative 9.81, right? Even though the velocity differs a lot, or is sometimes even zero, the acceleration is still instantaneously negative 9.81. So you have to keep this in mind. A stone is thrown vertically upwards. A student plots the variation of time with its velocity. Again, this graph, student, ball, vertically upward, right? This is the point zero, where the velocity is zero, and then velocity starts to become negative. So this is a what, by the way, what is the vertical displacement of the stone from its starting point after 5 seconds? Now, this is the 5-second mark. So the displacement, there are two types of displacement here. This is positive displacement when it goes up, and this is negative displacement, right? So, for example, if the ball starts here, the positive displacement is, let's just calculate this, 3 times 30 times 1/2, right? So 45 meters, right? Yeah, 45 meters. So this displacement is 45 meters. Now the ball starts to come downwards, and we have discussed this, that the displacement is the final shortest length that the ball is displaced, right? So we have to consider this one as well. So this is 2 times what is base 20, right? Because we know it's negative. Right now we're not writing 20, so this is 20 meters. So the distance that it comes down is 20 meters, right? So this is 15 meters, 25 meters, I'm sorry. This is 25 meters, that it's still above its position, right? Let me draw this one more time with some correct metrics. This is 20, right? And this is the position of the ball. Just imagine that it's directly above this, so because I want to draw it correctly. So first it went upward of 45 meters. Then till 5 seconds, it came down 20 meters. So the displacement between here and here is 25 meter, right? So this is the final displacement. Even though it has traveled the distance of 65 meters, the displacement is only 25 meters. So this is the answer. Now, this is also a nice question. A car travels anti-clockwise along the circular road of 12 meter, right? Radius 12 meter as shown. The car takes 4 seconds to move from P to Q. So it goes all the way from here to here to here to here and comes here. What is the magnitude of the average velocity of the car from P to Q? Now, a common mistake here is that people try to calculate this circumference and then find the velocity. And that is okay, but if you're finding the speed, but right now we're finding the velocity. So the distance that we have to put, displacement that we have to put in the formula is this, right? So this is the hypotenuse of this right angle triangle. So this is also 12 meter radius. So this is under root 12 square plus 12 square, right? So its magnitude becomes, let's just write 12 root 2 right now, full form. Now, this is the displacement, right? This is the distance that it has covered, but this is the displacement. So velocity is displacement per time. So 12 under root 2 divided by 4 seconds. So it's 3 under root 2, or I'm sorry. Yeah, 3 under root 2. 3 under root 2 becomes 4.2. So this is our answer, right? Now moving on to the sixth question. The water surface in a deep well is 78 meter, right? 78 meter below the top of the well. So let's just draw a well here so you can understand this better. So this is the well, and this distance here is 78 meters. A person at the top of the well drops a heavy stone down the well. So the stone is dropped from here, right? Air resistance is negligible, so we don't have to consider this. The speed of sound is 330 meters per second. Now, what is the interval between the person dropping the stone, right? Interval between the person dropping the stone and hearing it hitting the water. So the first time you have to consider is the stone reaching the water here, right? The stone reaching this is the first time that you have to consider. And the second time that you have to consider is the sound reaching the top. So let's just take the first time, which is U is equal to 0, right? S is equal to 78. A is equal to negative 9.81. And we have to find T, right? Time. So the equation that we have to put here is S is equal to UT plus 1 over 2 AT whole square. So this becomes 78 times 2 divided by negative 9.81, right? Okay, so the displacement is also negative. We have to put this negative because it's a downward displacement and we've taken the downward direction to be negative. So we have to put this minus sign here. And this is all under root, right? Is equal to T square under root, which cancels out. So this T becomes, let's just calculate this in 1 second. So this time is 3.988, right? This is the time 1. Now, this is not our time because another thing that is happening after this is the sound reaching the top. So just apply the speed formula. Speed is equal to distance over time. So time is equal to distance, which is 78, and speed, which is 330. So this time is So this time becomes 0.236. So adding these two together is the time, is the interval between dropping the stone and hearing the sound. So add these together, 3.98878. Yeah, 88. So this becomes 4.22. So this is our answer, 6. Yeah, 4.22. Now, a ball is thrown horizontally with a speed of 10 meters per second above the horizontal ground. So, for example, this is the horizontal ground. This is the ball thrown at 10 meters per second. The ball hits the ground, right? It will take a parabola path and will hit the ground in 3 seconds. So the time it takes here is 3 seconds. Now, air resistance is negligible, so the speed of 10 meters remain constant. The horizontal speed of 10 meters remain constant. So just have to find the speed of the ball just before it hits the ground. So the speed of the ball refers to the total velocity of the ball, which would be in this direction, right? Because it will have a downward component at the end and the vertical component, horizontal component, which would be 10 meters per second, right? Because the horizontal is air resistance negligible. So we just have to find this, and we can find this answer with Pythagoras theorem. So how do we find this? Use a equation of kinematics. U is 0. V is something we need to find. T is equal to 3 seconds, right? And another thing that we have is acceleration, which is negative 9.81, right? So V square is equal to U square plus, no. V is equal to U plus AD, right? This is the equation that relates all these quantities together. So V is equal to U is 0. So negative 9.81 multiplied by 3. So V is equal to negative 29.43, right? This is the V, this is the horizontal component. And it's negative, so you know it's downwards, right? Even you knew this even before solving the question, but it's nice that the equation gives you the answer as well. So this is our head to tail diagram, right? 10 meters per second. So this would be our speed or our answer. So squaring these up and adding these together would give us under root 966, right? Is equal to answer, and answer becomes 31.1. So 31 is the answer. So that is total speed. Remember to account for both the components here and not just one of them. The curved line PQR is the velocity time graph for a car starting from rest. Now, the average acceleration of the car is the first 5 seconds. Now, acceleration is always given by the gradient, so just cancel out the options with the area written on with them, right? Because we are not dealing with area right now. So the gradient of the straight line PQ or the gradient of a tangent at Q. Now, which one do you think it is, right? Which one do you think is it? It's not the point at point Q, because this is the instantaneous acceleration, right? Because it's the acceleration at this specific time. If you want to find the average acceleration, this line would give you the proper gradient and the proper acceleration. So C is the answer. So this is it for our practice for P1. Remember to check out the P2 video as well. I hope you learned a lot from this video, and subscribe if it helped you. And thanks for watching, and goodbye.